Hi, we're the Microplastics, and today we present you the MagnoFilter. Microplastics pose an uncertain danger to our ecosystem, as scientists now estimate over 8 million plastic particles per meter cube already exist in our oceans. These reach bodies of water largely through untreated sewage water, where rainwater can wash up tens of thousands of microplastics from car tires, oils, and plastic litter. We have identified magnetic extraction as a viable solution to deal with high-flow contaminated water. This method consists of combining iron nanoparticles with hexadecyl trimethyloxysilane, or HDTMS. HDTMS provides the iron particles with hydrophobic tails that can easily bind to plastics by hydrophobic interaction. These hydrophobic tails are particularly effective in trapping plastic particles as small as 10 micrometers up to 5 millimeters. Once trapped, the microplastics and bound iron nanoparticles can easily be recovered by magnetic attraction. In terms of effectiveness, magnetic extraction of microplastics has been proven to be highly effective. For contaminated water, it has been shown that at least 76% of plastic particles, depending on their type, can be removed using this method in 120 seconds or less for still water. For polyurethane, the efficiency is upwards of 95% of microplastics removed. So, we can conclude that this method is particularly effective as a standalone process in plastic filtration to create clean, drinking quality water. With this technology in mind, we created the MagnoFilter. The cylindrical device is to be placed inside sewage outlets and secured with large industrial screws. The key aspect of our design is modularity. Its diameter and length follow a 1-to-1 ratio and can be easily manufactured to order to make it compatible with any circular sewage outlet. For our initial model, we used a 60-inch diameter and 60-inch length to fit the most common outlet type in the New York City metropolitan area. Water enters the device from the left, where a coarse mesh filter stops large debris and litter from flowing further. Then, the iron nanoparticles are released into the flowing water and are allowed to mix with the water before entering the following section. Next, once the nanoparticles have bound to microplastics in the stormwater, they are attracted to neodymium magnetic fins, where they remain until the next cleaning cycle. The boomerang-shaped fins are hinged at the center and have the capacity to fold with high water pressure in case of high flow rates, to avoid flooding of the sewage system. Lastly, clean water exits the MagnoFilter on the right before joining a body of water. We have worked around multiple design constraints to create the most effective solution possible. From our fluid flow analyses, we estimate that we will be able to remove 60 to 80% of microplastics in the stormwater, depending on the flow rate we are dealing with. The use of our high surface area fins ensure that all of the nanoparticles, bound or unbound to plastic, are retrieved. The fin design makes it suitable for variable rainfall and flow rates, and targets regions where sewage infrastructure already exists. It is easily scalable to fin sewage outlets of 24 to 60-inch diameters. The high water to magnet surface area ensures that all injected particles are retrieved before the water joins water bodies. In terms of maintenance, our design allows the MagnoFilter to be removed for cleaning with ease, with maintenance likely to be required every 3 to 6 months to refill the iron nanoparticle distributor and clean the magnetic fins. We estimate that the manufacture, delivery, and installation of each device to be somewhere between $1,000 and $2,000. However, with this price tag comes along the consideration of a very high efficiency and lifespan. We estimate that a single MagnoFilter can remain in operation for over 100 years, until the neodymium magnets begin to lose their strength. In conclusion, our solution will help remove upwards of 60% of microplastics washed up from stormwater using magnetic extraction. We have considered every number of design constraints, such as high flow rates, water contamination, manufacturability, and lifespan, to produce a long-term, high-quality device that will change the flow of our future.